Hey everyone, what's going on? Welcome to Focus AI. So here in this video, we will see a code example of KNN, how you can leverage the KNN model to do a classification example. So this is Google Colab. It's similar to a Jupyter notebook. You can do the same thing in Jupyter notebook as well as in a Python script as well. Okay. So the first thing or the first package we need to leverage here for applying KNN model is the Scikit-Learn package. Now, basically in Google Colab, we have the Scikit-Learn package built in previously. We don't have to install it. But sometimes what happens is that the version of the Scikit-Learn might be very old. So it's always better to pip install upgrade the package name here. The package name is Scikit-Learn. So it will be upgraded to a to the most recent version. Okay. Okay, so once the package has been updated, we have to import few things. Like these are the things for fetching the data and plotting. So pandas, numpy, matplotlib, and scikit-learn, the package itself. Now for getting the dataset, we'll be using scikit-learn dataset module to import the breast cancer dataset. Okay, so this is a binary classification dataset, and it's a famous dataset, preferably a small dataset, but it has it has quite a few number of data points. Okay. Now for pre-processing, we'll be using standard scalar, train test split, and KFold. All are available under scikit-learn package. And for modeling, we'll be using the K neighbors classifier. Okay. So anyway, we will go through each one by one, and I will let you know how you can use this. Okay. So the dataset. So the dataset is the breast cancer dataset we are using. It has two classes. Okay. So the classes are M and B. M for malignant and B for benign. Okay. So it's a type of cancerous cell specifically. So you have to predict, like, given some features of a unknown patient, we have to predict that whether the breast cancer is a malignant or a benign one. So the distribution is like malignant data points are around 212 and benign samples are around 357. And the total samples are 569. And the feature dimension is 30. So for each data point, it has 30 features, 30 dimensional feature vectors. Okay. So how we can load the data set? So we have to call the load breast cancer data set. Okay, this particular class we have to call. Okay, now I am just giving asframe equals to true and return xy equals to true, so that it will return a data set which is a type of tuple. Okay, once we unpack the tuple, the first element will be a featured data frame, and the second element of the tuple will be the label. The label will be a series. Okay. So once the data has been loaded, we have to analyze the data. So using the feature data frame dot head, you will get the top two row, the top not two rows, actually top five rows. Okay, top five data points, and all the feature names you will get to see. Like there is mean radius, mean texture, mean perimeter. So all these are domain specific data set used in medical science or specifically in breast cancer. So a domain expert can explain this much more. But like that, we have a total of 30 features for each data point. Okay. So once we have seen the of sample of the data set, now you can get very basic statistics of the feature by using the dot describe method. Okay, so what are the statistics it would give you? It would give you count, it would give you mean, standard deviation, the minimum value, the maximum value, 25th, 50th, and 75th percentile values. So all it will give. Now if you don't know any of this, don't worry, I will be having a separate statistics and probability video tutorial where I will explain all of this into much details. Now, these are the basic statistics. Like mean is the average, standard deviation is the actually how sparse the data is, what is the variation in the data. That is, this is the minimum value, this is the maximum value. All these things are there. Okay. Now, if you see carefully, like some of the features are having in the range of tens, like 28, 39. Some are in the range of hundreds, like 188. Some are in the range of even thousands, like here 2500. Now, these some of the features are in the range of 1/10 or even 1/100th also, 0.09. Okay, so now you can see there is a huge difference between the scales. Some features are in the range of thousands and some features in the range of 0.09, something like that. So there is a very proper technique called standardization. We will do that. Okay. Okay. So before that, just check the label also. So as I've said, it is a binary classification. So malignant and benign are the two classes. Okay. So if you use the dot unique method on a series, it will return you the unique values in that series. So binary classification, so there will be two unique values, 0 and 1. 0 might be declaring as, I guess, malignant, and 1 is declaring it as benign. But anyway, so let us show you visually, like how does the data distribution is showing here. Okay, so the data distribution means that class distribution. Okay, it is specifically the class distribution. So here you can see the zeroth class. That means the benign class are a bit high, or the number of data points are more than the malignant ones. Okay, so this is kind of an imbalanced data set. There are some ways by which you can handle imbalanced data set. But anyway, for the time being and for this tutorial code walkthrough, I'll be ignoring this. Okay. So anyway, so this is how you can check the class distribution, whether the data is balanced or not. So now coming to the data pre-processing. So yes, what I was actually saying, that there is a scale difference in the feature data. So to minimize the scale difference, or to do kind of balancing so that every feature falls under the same scale. Okay, so for that you have to do data standardization. So in simple term, data standardization is that it standardizes the data and keeps your feature data, all the features data, into a same scale. Okay, so there is a dedicated video on data standardization or feature standardization. You can go and check. In a more depth, I have shown you like what standardization mean, how you can do that. So here, this is the general idea. So how you can do the data standardization. So in Scikit-Learn preprocessing module, it has a standard scalar class. You have to just initialize that class. You have your feature df, feature data frame, fit it, and then just transform your feature df. So all those level differences will be vanished and all the features will come under the same data, in the same scale. Okay, now if you do after standardization that what are the values by using the dot head method, you will see now that almost all the features are in the same scale. There are no such features which are much higher. There are no such features which are much lower. Okay, so all the data sets are in the same scale or in the same range. In simple sentence. Okay, now you can check the same thing using the describe method. Now you can check like the any of the value, check the maximum value or check the minimum value. Both are in the same range for all the features. For all the features, both are almost in the same range, you can see, right? So that means your features have been standardized. So it's always a good practice that whenever you are using any machine learning model that deals with any kind of distances, it's always best practice to standardize your features. So here we are using KNN, and as you all know, KNN is solely dependent on distance matrices like Euclidean distance. So it's always good to know that why uh, feature standardization is needed. Because okay, anyway, like how distance affected due to feature standardization, I have a dedicated video on that. You can always go and check that. But anyway, here we have to do feature standardization because we are using KNN, and KNN solely depends on distances like Euclidean distance. Okay. Okay, so once the data standardization has been done, now if you remember, we have to split our data into train and test. So for that, we'll be using train test split, this method, which is available again under Scikit-Learn. Okay, you have to give your feature data, you have to give your label as well, because this is the input, right? This is the input and this is your output, right? So it is a classification, that means supervised learning. So you need both input and output. So you're providing your feature data, which is input, and label, which is the original or the actual output. Okay. Both the features and labels will be split into train and test. Train and test. So this is the feature train, this is the feature test, this is the level train, this is the level test. Okay. Now, if you remember in my theoretical tutorial, I have told you that uh, there are many ways to split the data, and one of the broadly used, uh, this broadly used technique for splitting the data is randomized splitting. So this is a randomized splitting. Okay. So here we are giving test size as 0.3. So it will shuffle the data, shuffle both feature data and the label data, and then from there it will grab 30% data for test and rest 70% data for training. Okay. And random state 42, it's always good to give a particular random state or maintain a random state throughout your project, because it gives you reproducibility, because this splitting is happening randomly. So if you don't give any specific random state for the first time, the way it will be splitted, the next time it won't be splitted in the similar way. So if you give random state and if you maintain that particular value, so whenever you will run, you will get the exact same data. So for reproducibility, it's always better to choose a particular random state. It is an integer. If you don't give anything, it will take the timestamp from your operating system by default. So every time the timestamp will be changed, every time a different type of shuffling and randomized result or randomized splitting you will get. To maintain that reproducibility, you need to give a particular random state. It's an integer value. Okay. Okay, so once you have split your data, now if you remember, we have to find the best k, right? So for that, one of the strategy was to resplit the training data further using something called KFold cross validation. Here, this k is not the same the k in KNN. Okay, so this is like how you want to resplit your training data in how many chunks? In k chunks. So I am here taking as k equals to 3. So our training data will be splitted into 3 equal chunks. Okay. So how you can do that? First, you have to create a object of KFold class with giving like the number of splits you want. Here the number of split is 3 because I have assigned k as 3. Shuffle true, that means even while shuffling, even while k-fold thing, cross validation thing, you have to shuffle, you will shuffle the data, and again, as it is shuffling is a random process or randomized process, I am giving the random state again as 42. So I have chosen 42 as a number. You can choose anything, 1, 2, 5, 0, anything, but you have to keep it a single number every time when you are using random state or randomized process. Okay. So we have created this k-fold. So it will be used later while the tuning of the process. So let me show you what is called hyperparameter tuning. It is nothing but finding the best value of k. I told you k is a hyperparameter for KNN. So tuning the hyperparameter means we have to find the best value of that hyperparameter. That means k. We have to find the best value of k. Okay. So what I am doing is that first I am creating a list of k values on which I will try a loop and check like for which k value is we are getting the best performance. So here I am taking k value starting from 1 to 30. Rather, I guess it would be 29. Yes, it would be 1 to 29. Okay. Now again, it's always good idea to take odd values. I have told you why, because if you are taking even value and if there is a tie, then the majority vote won't be happening and the model will give you random results or random predictions. So always it's better to choose a series of k values as odd numbers. But here for simplicity, I have chosen from 1 to 30, odd and even number as a whole. But in production, always try to choose k as odd. Okay, so once this is done, now our main code, now our main code for hyperparameter tuning is happening. Okay, so what we are doing, I am just defining three lists. Okay, the first one is the validation accuracy. For each k, I will be appending the validation accuracy in this particular list. Then training error. Okay, now for each k, I will be appending the training error in this list, and similarly validation error. So I will show you the plot I have shown you while in the theoretical tutorial. I will show you in practice that yes, we can plot the same thing and we can infer the similar kind of idea that we actually covered in our tutorial. from the theoretical perspective. Okay. Now, first, the for loop is that I'm iterating through each of the k values from 1 to 30, rather 1 to 29. Okay. I'm initializing validation accuracy as 0, validation error as 0, and training error as 0. Now what I'm trying to do, now the cross validation is happening. So we have created a cross validation object, right, named KF. Okay. Now KF.split xtrain. So what it is actually doing, it is resplitting our training data into k chunks. For our case, it is 3 chunks. Okay. So the every combination of training chunk and validation chunk will be given here as the form of index. So here this is the training index, here it is the validation index, and for every combination it will give us. So from the actual X train we can get the cross validation training and validation training feature data, and cross validation level and cross validation level we will get from this training index and validation index. Okay. So once we get the cross-validation training data and validation data, we will use the k-neighbors classifier that we have imported in the first cell. So it is the main KNN algorithm. We are actually initializing a KNN class, and we are saying that okay, we will be taking the number of neighbors as k value. What is this k value? K value is 1 for the first iteration, then 2, then 3, up to 29. For each and every k value, we will create a k neighbor classifier and we will try to check what is the performance. Okay. So we have created a neighbor or k neighbor classifier or object. Now we are fitting. Fitting means the training process. Every time you learn fit or every time you heard fit, that means training process is going to occur. So on which we are going to train? On the cross-validation training data that we got from here. It's not the actual training data. Actual training data is xtrain. Okay, but after doing the cross-validation, we are getting two chunks, one for the training and one for the validation. So we will be training using the cross-validation training data, and we will provide the actual cross-validation level or the true cross-validation level for training, obviously. Then we will get the validation accuracy from how? Once it has been trained, this particular neighbor object has a score method where you will give the validation data, both the validation features and the validation level, true level. Once you will give that, it will return an accuracy score between 0 and 1. So 0.8 means 80% accurate. Okay. So you will get validation accuracy. Similarly, you will get validation error. How you will get validation error? Just simply uh, subtract the accuracy score from 1. That is the error, right? If there is 80% accuracy, then error is 20%. If there is 100% accuracy, then error is 0%, right? And how you'll get the similar training error? Similar, you have to subtract your accuracy score from 1, and here for calculating this accuracy score you are providing the training data itself. Training data means the cross validation training data. Okay, both the features and levels. Done. So you got everything. You get validation accuracy, you get validation error, and you get training error. Once this inner for loop is done, that means that all the cross validation combination has been iterated over. So you will actually populate all this list: k val accuracy, k val error, and k train error. And what will be the appending value? It will be the average. I said that if you remember, if you just go through my previous video how cross validation works, we have to append the average for all the cross validation data. So that's why I'm dividing it by k, because for cross validation we have chosen k as three chunks. So I'm dividing it by 3. So we are getting the average validation accuracy, average validation error, and average training error. So once this has been done, a particular iteration of k is done, right? A particular iteration of k is done. So I have just logged it using a print statement. So once you will run, it will be like training done for k equals to 1, equals to 2, equals to 3, up to 30. Okay, up to 29, right? Yes. So once it has done, now you have to find out what is the best k out of 1 to 29, right? How we can do that? If you remember my previous theoretical tutorial where I have said that you can find out k from two things visually, By plotting the validation accuracy or by plotting the validation error curve, right? We will see both. So let's plot the validation accuracy plot first. Okay. So this is the validation accuracy. So I have shown you that the validation accuracy curve will be something like that. First, it will be increased and then it will decrease. More the k will increase, the validation accuracy eventually decrease up from a threshold point or a certain point. That particular threshold point is the best value of k. Now here you also see a similar kind of pattern. Now it won't be exactly that much smooth, but a same kind of, like, for smaller values of k, it tried to increase and then after some threshold point it is decreasing. Similar kind of pattern you can see. So this threshold point is actually the value of k. Okay, so this is by validation accuracy. Now see the validation error and training error. Okay, so again, if you remember, I have shown you how the error curve will be something like, if it is k in x-axis, okay, then the training error curve will be something like this. The more we increase k, the more the error will be increased. So this is error actually. In y-axis, it is error. Okay. So the more the value you increase for k, the training error will be increased, and more and the validation error will be something like that. First, it will decrease, and after a threshold point, it will again increase. Now, this particular point will be our best k. Right, because here the validation accuracy is high, that means the validation error is low. Now you can see a similar kind of, this is actually this blue line is the training error. Now if you see, it started increasing and increasing and increasing, the more you are increasing the k, right? And the validation error is, it is started decreasing and then started to increase. So this is our actual k value. Now from the plot we can see that, okay, this point will be our k value. But how to get that exact k value? It's simple. We have a list. We plotted this graph from the list of the validation error or validation accuracy or training error, right? Now we can get the maximum value. We can get the minimum value of error, and based on the index we can get the k based. So what we have given, this is the validation error list. From that list, I want to find the index value. For what index value? Where this validation error has a minimum value. Because, I mean, the validation error is minimum, that is our k point. So first we are getting the index, and using the same index, I am fetching the best k. Now if you check, the best k is 5. And the validation error at best case is 0.04, quite low. Now once you get the best k 5, now you actually train your the final model. The final model is again K-Near's classifier. Now you are saying that now we are not iterating. Now we know the k based value, which is 5. So now we are training our final model with number of neighbors as 5, and then you fit on the original training data and original training features and original training levels. Now we are not using any cross validation data. Once we get the base value of k, we will train with our original training data, and then we will be using the test data. Look, I told you the test data will be kept separate. Throughout this process, we never use the test data. Only for the final model, to validate the model, we have used test data, and we are getting a pretty high score, which is 95% accuracy. So this is it. So in the entire video, the KNN classifier or KNN model is only this much lines. Just see, only these 3 lines, right? We have learned several videos to learn how KNN works from the theoretical perspective. But in practice, using Scikit-Learn, it's this 3 line. First, you initialize the KNN classifier with the number of neighbors. Then you do the training. Fitting means training. Dot fit means train. Once you are done training using the test data, you get the accuracy score. These 3 lines. And we have done almost 10 videos, right? From theoretical perspective. Now you might have a question like, then if it is so much easier using Scikit-Learn, then why is the need to learn the theory from the theoretical perspective? Why do you need the concept, right? Okay, yes, you have two choice. Either you learn theory and then apply it in practical, or you don't learn anything from the theoretical or conceptual point of view. You have Scikit-Learn like high-level libraries, and you can use it directly. Then there will be a difference. Let me give you a couple of examples. Here we have used a fairly toy data set, a small amount of data set. But now if you are trying to build a model in production, and you have a data set of having, say, a 10 million data points, a huge data set. Okay. And the feature dimension here, it was 30, right? We have seen it was 30. Now you have a feature dimension of, say, 1000. Okay. So 10 million data points and 1000 feature vectors. That means 1000 dimensional vector. Okay. Now you are writing KNN. Now you can easily write. You have to just write these 3 lines of code. Okay. You have your training data, you have test data, you just write this particular code and you are done. Now, I will surely say that that would be a mess if you deploy it. It won't work. It won't work. Why? Because that's where the theoretical concept will be there. Because first of all, if you don't know that the memory and the time complexity of KNN, okay, then you will directly write this model. Okay, if you know, then you might not go for KNN, you might go for some other models which will where the time complexity and space complexity is much lower than KNN, right? So that is one thing you have to do when you have the theoretical knowledge. Okay, second thing is that you have 10 million rows, and in 10 million rows, forget about the space complexity, it will need some GBs of RAM. But there are some theoretical perspective by which you can drastically reduce the time complexity, right? You can drastically reduce the time complexity. Okay, I have shown you how you can either use KD tree or you can use ball tree, right? if you don't know if you don't know those theoretical concepts, you will directly use the brute force method. But if you know, then what would you go? You will change the algorithm to either ball tree or KD tree. But those who don't know the theoretical perspective, they will simply use the brute, right? They don't know what is ball tree, what is KD tree. They don't know actually, right? So that is one point. Now you have high dimensionality. Okay, in high dimension, Euclidean distance does not work properly. You know theoretically that Euclidean distance doesn't work properly. Which distance does work? That is the Manhattan distance. Now, those who don't know the theoretical perspective, they will directly use the Euclidean distance because the default value of P is here 2. If you remember, means Minkowski power is P. If P is 2, that is Euclidean distance, and it will be a mess for a 1000 dimensional data. But if you know the theory, you will just change this 2 to 1, and it will become Manhattan distance, and it will work quite finely. So there are many examples I can give you. That's why you will not be a software engineer, you will be a machine learning engineer, where you have to be as much as strong from theoretical perspective and applying those concept into, so as a in a engineering in a practical perspective. So that's why both theory and practical is much needed, both needed. Otherwise you will be a software engineer, right, where you don't have to know what to use, why to use, and when to use, right? So that is the thing. So I think it's a fairly good code walkthrough of KNN. I will surely share the whole notebook, the link of this Google Colab notebook. You can download and you can play. You don't have to download, it will be open in your Colab environment. You can directly just use, you can play with that, you can plot different diagrams and everything. So anyway, this is the end of this video. If you like this video, then do subscribe my channel for the future